Welcome to the webcast series Locker Talk, brought to you by BreachLock, a global leader in attack surface discovery and continuous pen testing and red teaming. Today's webcast is Behind the Breach, Web Applications and API Hacking, where we will discuss the transformation of modern web applications and demonstrate how attackers are persisting in uncovering and exploiting vulnerabilities despite the advancements in technologies and new innovations. This is part 2 of a 2-part series, and both part 1 and part 2 will be available on demand at the BreachLock website after this airing. Our guest speaker today is Mitchel Koster, the Chief Security Researcher at BreachLock. Before joining BreachLock, Mitchel worked as a red teamer at ING Bank, bringing expertise in hacking and software development. He holds credentials in both an offensive security certified professional and as an offensive security certified expert. Mitchel leverages his expertise on the client side in software development and embedded devices to lead advanced penetration tests and drive cutting-edge research and security automation. Thank you for joining us today, Mitchel.
Thank you, Anne. Nice to be here again. Looking forward to getting into part 2.
There you go. All right. And with that, I am going to turn it over to Mitchel, and he's going to present part 2.
All right. So this is the second episode of Behind the Breach, Web App and API Hacking. As I discussed last time, this heavily revolves around understanding web vulnerabilities as well as how to patch them, right? Because the best way to understand them is to figure out how they work, how hackers exploit them, and then what you can do so you can best decide what fits for your scenario. So a quick summary of last time for everybody that's joining new. Last time we discussed the evolution of vulnerabilities and mitigations. We discussed cross-site scripting, cross-site request forgery, as well as various password reset vulnerabilities, what the problems are, how they exist, and how you should prevent them, as well as the importance of knowing your tooling, utilizing it correctly, and making sure that your juniors are also aware of the more technical implementations underneath of the abstractions that your framework might offer. So we'll be starting this episode off with mass assignment. So a mass assignment attack in particular is when through any means or form an attacker is able to add more parameters to an object than they are allowed to, often in sensitive fields such as passwords or emails or even roles, right? And this demo environment will be a simple user profile management application where you can again update a profile, but other than just changing maybe the name or changing your email address to a new one, you can also secretly inject a role into the profile change, meaning you can make yourself an administrator. And this can be patched in 2 different ways. Typically, right, one would be protecting the data models that you're using for your database communication, and the other one would be a very strict user authorization, something we often see issues with. So for those not familiar with the first episode, we have a interactive demo environment, which will take a second to spin up. We typically create an account when we first start, so we as an attacker get access to the website we want to hack, and then we proceed to demonstrate the vulnerability, patch it, and then again show that it's patched by trying the same attack again. As you can see, there is many users here that we could target, but we are going to start off with our own user, where we are helpfully reminded that our current role is a user. If we inspect the API call that happens in the background, we can see again that it says our role is user. This is vital information for carrying out this attack because you know the structure of the user object. And if we look at replaying this request, this will take half a second because I've created a script to conveniently done so. What this script does is it will make a update request to a profile and change the role of any user to admin, because we now know the format of the role, as long as we know the ID of their user account. And of course, we need an active token from a logged in session. So what we do here is we first have to provide our current web token that we can use to communicate to the API. And once we have that, we have to provide a user ID that we would like to target, in this case, our own. And once we execute, we can now see in the response that our role has been changed to admin or administrator. And if we refresh the page, we can see the same. So it is updated in real time. And we can now do a lot more on the website in theory. To test if authorization has been done correctly, we can also try to do this on a different user on the website. So again, we'll take a user at random. In this case, user 1, Angela Calls. And we changed her role to admin. If we refresh, you can see that not only can we escalate our own privileges, we can do this for any user. And the same holds true the other way around as well. We could make the existing admin a normal user and gain full control of the application while locking the admin out. The first solution to this, or a solution, would be to add some proper authorization, right? Where before you perform an update request, you have to make sure that you're performing it on your own user. If we now try the same attack again on a random user, you will see that we are not authorized. So we can still update our own role, but not that of a different user, even if the attack, the mass assignment attack itself has not been modified, solved. Most frameworks will have some form of guarded and fillable fields, right? Guarded meaning which values should we protect or not, right? And in this case, you saw that we had a fillable property, meaning prior everything in the user object could be updated. But if we say we want to specify which fields should be fillable, like in this case, the email, name, and password, only those values can be updated. So in this case, the role is no longer there. If we now create a new user, which would again by default have user privileges, and we try to do the same attack again on our own user, we would no longer be able to become administrator because we are not allowed to modify that property. Right. The second one for today is insufficient rate limiting. Right? Rate limiting is very broad, but in this case, you can decide, right, how many requests a user is allowed to make in a row. It's normal for somebody to make a login request, maybe get it wrong once or twice, right? But when somebody makes 50,000 login requests within 2 minutes, that's way too much, right? We see all kinds of rate limiting issues in reality, but one of the more painful ones is where rate limiting is not properly applied to external things that cost money, such as an SMS gateway. Like you can, and as a company, send text messages through your website, which maybe cost 5 or 10 cents per text to send, right? And if I, as an attacker, can just endlessly spam that over and over and over, the prices will rack up pretty quick. And that's what I'll demonstrate, right? As far as how to patch these kind of things, there's multiple solutions. The most obvious one would be rate limiting. How you want to do this specifically could depend on your company, but you could do this per logged in user session or IP address, for example. Of course, adding adequate authorization, or you might even want to implement some sort of caching behavior. So we go to the same as usual. We create our new account and we see a new feature that will allow us to send a SMS message. Right? So I'll set up some logging and testing on the right-hand side so we can keep track of what's happening. And if I try to use this platform with my logged in session to send a text message to a phone number, you can see that one SMS has been sent on the server. Now, from the attacker perspective, we'll do something similar, right? We want to automate this process so we can simply do as much damage as possible financially. So this script will keep sending the text message to 5 phone numbers at the same time and send a request every second. And you can see this racks up pretty quickly. Now imagine that we do this for 24 hours straight, perhaps from multiple computers. So as far as patching this goes, right, the first patch would be to perform some sort of rate limiting. In this case, the framework has a built-in throttle method, right? But most frameworks will have some form of rate limiting middleware, where I can say I want to only allow so many requests within 5 minutes, and beyond that, start throttling or do what I would want to do. You can specify the behavior, and you can see because we had already sent requests, we are now met with a failure to send. It will send the first 4, and at the 5th it will say rate limiting essentially. Just to show some more means of doing this, right here we have a custom addition to the middleware where we will only allow a message to be sent to a phone number before shortly being cached, right? And only after a few minutes can it be sent to the same phone number again, just to show some variation of what you can do, right? And of course, do this to your company's needs. You can see it sends it fine the first time, but then because text messages have already been sent, it doesn't get sent again. And sometimes patching can also just be that simple. Again, a very common one with a very fancy name, insecure direct object references, right? Really means that you can typically enumerate a URL, an object, or whatever else by guessing IDs and whatnot to try and identify sensitive information. So for this demo environment, we will have a website that stores personally identifiable information, or more particularly an API, which has profile information on a user, but that profile information also happens to contain credit card data because the API is oversharing too much. This can be patched again by user authorization. Should I be able to see information from all users, yes or no, right? And secondly, by limiting what the API shows, which can be done on request basis or global. But I'll show that in a second. And this is a simple but a very common one. Right. So after some setup of the application, we are now dealing with an API, and the API token will be displayed to us on our home screen for ease of use. If I look at the original API request that's being made, I can see it requests information for my user, which is a user 101. And within that, I also see a credit card field, which just happens to have no information in there for me. So then the question, of course, is what happens if I start requesting profile information for other users, my day of credit card information. And I wrote again a script for this to demonstrate. All I have to provide is again the session of the API token I would like to use, and we'll start enumerating all users on the websites and dumping their credit card data. And in reality, we'll see this often with signatures, with passports. We've seen it all. And this is an example of grabbing one of the requests where you can see the credit card number. So now going on to patching this, I said there were multiple ways of doing this, right? The first one being on the model level. And if you have data where you are sure that this should never be shown under any circumstance, you can always add it to a hidden field, which will prevent it from ever being serialized. Right? So now if we do the same thing again with one line of change, we have now stopped this entire attack in its tracks, essentially. Although we can still see all other users, we at least can very easily limit what data they get to see. And as you noticed, stuff like the password or memory token is also in there by default in this case. Any framework will have some similar feature to this. And the second one would, of course, be if you can't do this on global level, you can, of course, limit the response itself so that in this case it only gives back the username, ID, and email, but not the credit card token. It just requires a little bit more due diligence on the programmer side of things, but it will have greater flexibility. And of course, we cannot forget about authorization, right? Why can we fetch information for every user? In this case, maybe we only want to fetch it for our own profile and not that of any others. So again, just showing you various demonstrations, but use this up to your own requirements. And the mass attack now returns nothing at all. And now we have public data leaks via the public web route. Take public web route with a grain of salt. Just any publicly accessible files. Enter are many. In this demo environment, you'll have a website which seems to not host any files in particular. Nothing is glaringly obvious from the beginning. However, if you look a little bit like an attacker would, and you try to guess directories, etc., you'll quickly find that there is sensitive content, as well as a way to grab all of the source code from the website with all the history, extract secrets from it, and so forth. And I will show again 2 ways to patch this, right? And they differ depending on the scenario. One being on web server level and the other on application level. So what I'm trying to demonstrate here is we have no inherent access to the account. We cannot log in. We try to visit a registration URL. Think of your typical black box, just somebody on the internet trying to do harm, right? What an attacker would often do at this point is they would try to use various word lists, maybe Google references, to try and find any more content on your website. So in this case, we're using a tool called Koster that's covering more content. And we can already see that there is a .env file often used for website configuration, which in this case, once we download it, you can see it contains the configuration file of our Laravel installation, including the keys used to encrypt cookies, database connections, etc. And this could be a data breach just like that if you're unlucky and your database is public. We also find a backups directory with directory listing enabled, meaning we can see everything that's inside of there without having to guess it. And it has a database or backup SQLite file, a database, which we can then download and of course inspect for content. The entire database backup is now in hands of the attacker, and it's how a lot of database breaches take place. If we look at the content of the database real quick, we can see we have the entire database structure, but we can also import relevant data to CSV just like that. And we have a combination of email addresses and hashed passwords. Although hashed passwords are not necessarily directly usable, in this case, they all have the same password. So there's one hash, right? We can, of course, try to crack this using a password cracker, such as an attacker would. And it has been cracked successfully to decode to the password. Right? Secure password policies is a thing in and of its own. So now that we do have a list of email addresses and we have a password, we should be able to take an accompanying account and log in as a user despite not having any access before. And there you go. And of course, things could always get worse, as if having the environment file and all the past and the entire database content was not enough. If we go back to our content discovery, you will call it like that, you'll see we also have a secret folder, which seems like it hosts nothing. And it's a bit of a trick here. Normally it would be in the main directory, right? But in this case, it also contains the Git folder, which contains all of the source code, all of the history of every version of the source code, all of the developer comments, etc. So again, a hacker would use specialized tooling in this case to conveniently download all of the source code for this website. And this is really meant to be a bit more of a hands-on view of how an attacker would go about these things. And it will take only a second to download the entire repository, after which we can look at all the history of the code. And as you can see, at one point in time, we removed API secrets, meaning that prior to that, there were API secrets leaked in the source code, which is common. And we now find the API key super secure. It's a common way to leak source code credentials as well. So those were a lot of problems, right, bundled together, which have various means of patching them, but luckily they are not too hard. If you go to your website configuration, in this case Nginx, right, you can choose to specifically deny certain file extensions like .sql, .back, SQLite, etc., which would block us access from the database file that we had prior. This again would of course require a web server reload or reset. But now if we go back to the website and we try to access the database backup again, we are no longer allowed to. The website is blocking us. Of course, this is a very niche way of blocking specific file extensions that you don't want to be there, right? In some cases, you want to do this where you do want to host something, but it should not be publicly accessible. Or you could take more of a catch-all approach where you block any specific hidden file. In Linux, any file prefix to the dot being hidden, right? So this is more of a blanket approach. Right. So we go to the backups again, just to show that everything still works in the sense that it's blocked. It's done correctly now. The other issue is that you can still view which files are in directory, like the database backups. If you turn off directory indexing, right, it will not automatically show which files are in a folder if they are exposed at all. So if we go back to the database backups, and we now try to view the content, we simply just get forbidden. If we now try to do the same thing like we did before, download the Git repository, it will not be allowed either because we've just disabled access to anything prefixed with a dot, right, including the .git folder. This is a bit of a longer demonstration, but I think very worthwhile because this is often very sensitive data that we are met with and it's so easy to secure. Right. So I think adding to the last one as well, often a framework, and I'll take 0.5 seconds to show it because I think it's worthwhile. Every framework will by default come usually with a public folder, right? Meaning that even if you upload your entire framework and it's directly available, only the contents of this folder can be shown, right? You can't typically just download the rest of your framework unless you misconfigure a whole bunch of things or you use a less secure framework. Right. Going on to hard-coded credentials and secrets. I don't think this takes much of explanation because it's self-evident, right? You wouldn't believe it, but we find it very regularly, almost on a weekly basis, right? And for some things, you kind of front-end developers might not know a better way. For other things, there are leftover artifacts. But we have a demo environment that shows 3 different ways of accidentally hard coding credentials and or secrets, meaning to an API that you have a subscription from that can now be used by the attacker. It could be passwords, it could be anything. So the right way to deal with these kind of things is to make sure that the backend, right, so not your browser, but the server, deals with the secrets itself, right? And that any secrets that might be hard coded to begin with in the source code, right? Think of the previous example where we downloaded the entire source code repository. Stuff should not be hard coded there either. So you can use secret management or environment variables and to make sure to never enable any debug modes. All right. Having spinned up the environment again. One of the first things you might do as a hacker is just look through the general HTML source. And as you can see, there is credentials found right there. Now you might wonder how common is this? In reality, you see this a lot on internal applications or on acceptance environments where people are still adding new bits of functionality in, or they temporarily had to release a new form uh, while still offering support for the old one. You do see stuff like this more often than I'd like to admit. Right. In this case, the patch can be relatively simple, right? Because it's clear that the credentials might even need to be there, but need to be hidden. In this case of using standard HTML comments, you can use framework related comments for your view, right? Meaning that on the code end, they're still considered comments here. But if I were to look again in the browser, it does not get rendered. It does not show up. It's a safer way of doing comments. Most frameworks that offer a view engine of some sort will have something like this. Right. Moving on to another example here, right? If I first visit the page, you can see an API call happening on the background, and this could happen anywhere within your application, which calls, if you pay close attention, a different domain. Running on port 8000 is our application. Running on port 9000 is a fictive remote third-party API, right? Where we pass along a secret with a key that should be only available to us because this might be our paid subscription. It's not a point for the entirety of the internet to have this. And in this case, it's called traffic EX something. And in this case, the key is used to generate the quotes that you see on the home screen here. So what is the right way to deal with this is not to have the browser be responsible for making that call. And you can see the code right here in the front end for the browser. Simply delete this and change this for code that will call our internal API. Note the port 8000 that just requests a quote. Then we go to our actual server, the backend, right? Which will have a get quote functionality, which will actually contain the secret a little bit faster, which will actually contain the secret needed for the third-party API. So the secret is only known on your server now and not in the browser. Additionally, you can also see the actual secret API key that we have is not hard-coded either. It's being pulled from an environment variable. Of course, you can also use a secret manager for this, like I mentioned. Now, if you are to look at the browser again, you can see that we just make a call to our internal API, but the secret is nowhere to be found, thus an attacker cannot use it on your behalf. The last one is that we try to visit a page that does not exist, or we try to do anything that might cause an error. And before you know it, you get a full stack trace, you get weird error messages, or you get anything that might leak credentials, right? This is an over-exaggerated example, of course, but here what we see all of a sudden is a email address and a corresponding password. Again, it might be a bit over-exaggerated, but in this case, we could log into this just to prove the point. And this is often due to debug permissions on the application being too verbose. And once you're running in a production environment, you should not really have any debugging symbols left there, right? You should minimize the errors that you show. They should be generic. So in this case, this is simple as changing the configuration from enable debug to false, right? Do not enable it. And to prevent these kind of issues from sneaking in, using continuous deployment is really a nice way of doing it, because that way you don't require somebody to log in and update that file and possibly forget to do so. Right. User enumeration, and this is the last one that we have, right, for this session at least, is a way that an attacker can try to identify various users on the website, right? So we have an application with a login and registration portal where there is 3 different flaws, right? So we can identify whether a user exists through the forgot password page. We can do this through the login page, relying on errors, or again through the login page using a timing-based attack. The way to deal with this is to make errors that are very generic, right? So that for me as an attacker, it does not give more information than I need, but also to randomize responses on login requests just enough so that I can't draw a stable baseline to determine whether a user exists or not. This often happens because some login systems might have a back tie to a third party or to an LDAP integration, right, which might just take longer for a valid email address, even though the password might be wrong, than if you provide a completely fictive one. And in this case, to demonstrate the timing attack, I've hard-coded in a small delay to prove the point. All right, the demo environment is running again, right? We create a new account, so we have one account at least that we know that exists. This is required to get a baseline. If we now go back to the registration page or the forgot password page, sorry, knowing that test.com exists, if we ask for a password reset link, it says we have emailed your password reset link. So first off, this is already descriptive. It already tells me that it does exist, right? If I try this with a different email address, it will say we cannot find a user with that address. And this is like the most ideal way for an attacker, right? And imagine the impact of this on websites such as asklingmedicine.com, where anybody can just verify whether you are registered or not. There's a reason why those data breaches were massive. The same can be said for the login page. When I try to log in originally, it will say these credentials do not match our records because I provided the right username with the wrong password. If I try the same again with the correct password, we log in, right? Just to show how the functionality works. If I now try this a wrong password. It says again, these credentials do not match. We understand that much, right? And now if I try an email address that I know does not exist, again, to establish a baseline of behavior, we don't say these credentials do not exist. We say the email was not found. So those are already two different ways in which I can verify whether or not a user exists on the website. And one thing that has been missed here, because it kind of went too quick to explain, right? The reason I tried the same email twice is if you look at this login request, you can see it takes a very long time to take place, right? Because the email exists. If I were to try the same with something that doesn't exist, it goes by in a split second. And in the normal circumstances, as an attacker, you would write a script for this, right? So it will do the timing for you, and you can just say, hey, this request takes only 5 milliseconds. Whereas when I have a valid email address, even though the password is wrong, it will take at least 5 seconds, right? And if you try that a couple of times, you can establish quite a good baseline. So the first thing that we did here is remove our custom authentication message, right, for errors there. So we're relying on the framework again. And now, even if the user does not exist, it will say these credentials do not match. Additionally, we have to deal with the verbose error handling as well in the registration, right, where again, I had to add additional code to even be able to introduce this. We just simply remove it and we restore the original functionality. And now if we try this again, you'll get a more generic error, right? Saying that if it exists, something will have been sent, no matter whether the account is valid or not. That's the general recommendation. And this is to show the behavior around the timing. Because let me give some little more clarification there, right? I'm going there. Now, you can see that's the custom sleep that we had introduced, right? So we're removing this entire function for demonstrative purposes. And what we do now is we use the same rate limiting functionality like we used before, where we first off reduce the amount of attempts that somebody can make, right, to make it harder to establish a baseline in terms of how long does it typically take for a non-existing account versus an existing. But we also introduce a random delay of 2 to 5 seconds, which of course is an enlarged example, right? If you just make it big enough so that you can't establish whether an account exists or doesn't, that's more than enough. And usually you're talking 20 to 30 milliseconds in computer time, right? And timing attacks might not even be an issue in your point, and you can see it's delayed randomly enough that it's hard to tell whether an account exists or not. So that was the last vulnerability I had to show for this workshop, right? Um, I think if you have to take anything away, it's that things are changing very fast, right? And when things are changing very fast, a lot is forgotten in an attempt to keep up with all the changes. So as I mentioned in the very, very beginning, uh, understanding traditional vulnerabilities still provides value. Just because a vulnerability is old does not mean it doesn't exist. If anything else, because we always have a new influx of coming in junior programmers with more abstraction, the tooling becomes more important than the technique, and we keep forever introducing the same vulnerabilities, especially as the seniors who are to train the juniors are typically overloaded. mastering tooling such as your frameworks is important. A lot of these issues still persist, like I showed in the framework, right? Because people don't necessarily take the time to read the security notes on the framework or familiarize themselves enough to be able to know where the pitfalls can be in a framework. And the last one is really more for the pen testers amongst us. You've seen the evolution, you see where things are going, you see everything is turning into code. I personally believe that learning to program as a pen tester is a must if you really want to keep up with the ever increasing complexity of systems.
Okay, thank you, Mitchell. This concludes part 2 of this webcast entitled Behind the Breach, Web Applications and API Hacking. Again, I'd like to thank our guest speaker, Chief Security Researcher at BreachLock, Mitchel Koster. Again, this webcast will be made available on demand at breachlock.com. And if you missed it, be sure to watch part 1 to learn more. And if you would like more information about BreachLock and our offensive security solutions, please feel free to contact us at hello@breachlock.com. Thank you.